Welcome to part 4 of the series in simulating a supersonic rocket with ANSYS Fluent. For this video, we'll walk through the steps and considerations in setting up the simulation, including physics models, boundary conditions, and solution methods. If you've already been provided a prep geometry and mesh, or you're wishing to continue working on an existing case setup, you can launch Fluent from your Windows taskbar. For this simulation, we're using version 25R1. And when the launcher window shows up, ensure you're launching your simulation in the correct working directory. You select the number of processors that are relevant to the machine you're using. Double precision is selected, as well as the solution launcher is selected. And start. We can open an existing working case or read a mesh that's been generated from the File Explorer. Here, I'll read in the mesh that we generated in the last video. Again, the time to read this file will depend on the number of processors used and the total size of the mesh. If at first the red mesh is not displayed, you can select the Display Mesh icon and select the surfaces that you want displayed. The same Fluent mouse controls are used to manipulate the display in the viewport. Clicking the Display All Edges option, as well as creating a new surface plane along the midsection of the geometry, will allow us to better view the results and geometry representation. For any imported geometry, ensure to perform a mesh check to ensure the geometry and mesh were imported correctly. The Done tells us that there are no errors. Next, we'll change the units to the units that we want to use in our setup. Common changes are to specify your temperature in degrees Celsius and ensure that the length units are in meters. To set up a Fluent simulation, we'll use the workflow tabs and work from left to right and progressively set up the simulation, solution, and results. The same workflow can be seen in the tree view on the left. However, we'll be using the tabs on the top. The first step is to select the pressure-based solver and steady time stepping for the steady-state simulation. Ensure the energy equation is enabled and select the K-omega SST turbulence model with viscous heating and curvature correction to accommodate the high-speed flow modeling. By navigating over to the settings tree, we can confirm the model changes carried through in all workflows. Next, we'll change the models being used to determine the fluid properties. The density will be calculated using the ideal gas equation. Specific heat determined by the NASA 9-piece polynomial. And finally, the viscosity will be determined through the Sutherland equation. Using these models are critical to the simulation as they ensure that the fluid properties vary with temperature. Next, we'll set the operating pressure to 0 as is standard practice in compressible flow simulations and when using the pressure far-field boundary condition. For this simulation, we can neglect gravity as it is primarily a momentum-driven flow. Next, we can change the boundary conditions, where we'll assign the far-field flow a far-field pressure boundary condition, making the gauge pressure the atmospheric pressure at flight altitude. We'll also change the Mach number to the flight Mach number, ensuring to align the component of flow direction with our coordinate system. Here the coordinate system is not traveling in the direction of x, so we'll need to adjust to align with the z direction of flow. Finally, the thermal boundary condition will be changed to align with the air atmospheric temperature at 2 kilometers above sea level. Continuing to assign the appropriate boundary conditions for each surface, we'll notice that the inlet name selection was assigned a velocity inlet boundary type. We'll change that to pressure far field. And when you have multiple boundaries of the same type, instead of individually changing all of the inputs one by one, you can copy the inputs from a previous boundary and apply them to other boundaries of the same type. A double check of the boundary conditions for the inlet atmosphere showed they match the far field. We'll now set the boundary conditions of the nozzle inlet, which corresponds with the discharge of the combustion chamber. Thus, we'll use a pressure inlet condition, assigning the total gauge pressure to 4 megapascals, and the initial gauge pressure just slightly lower to 3.8 assigning the thermal boundary condition to 3326 degrees Celsius. And next we'll ensure that the automatic naming conventions assign the correct boundary condition of symmetry to the symmetry planes. And for the walls, the default values of zero heat flux and a stationary wall with no slip and standard roughness are applied to the wall boundary conditions. These are default values that do not need to be changed. And finally, we'll specify the outlet boundary condition as a pressure outlet with the same gauge pressure as the far field and inlet. Next, we'll set up the solution numerics in the Solution tab, selecting Methods. We'll use the coupled scheme, which solves for pressure and velocity simultaneously and is best used when these components are highly dependent on each other, as is the case in compressible flow. Green-Gauss node-based method is used for gradient discretization, and everything else is set to second order to reduce numerical diffusion. Ensure that pseudo time stepping is enabled, which automatically controls the time step in each cell, and enable high-order term relaxation, both for numerical stability. For solution control, we'll use the default residual limits to stop the simulation once an appropriate level of convergence is achieved. We'll use the hybrid method to initialize the solution, which populates the domain with starting values for the solver. The initialized domain values can be seen by creating a post-processing object, where here we'll view the contours of Mach number along the midplane. We can also readjust and set the default view in this post-processing object to align with our coordinate system. By inspecting the Mach number contours, we can see how the hybrid initialization method interpolates the starting domain values between various boundary conditions. Next, we can create report definitions to monitor the solution and assess convergence. For this simulation, we'll create a force report to calculate the net drag forces on the outer body of the rocket to monitor the design parameter of interest. Be sure to align the force vector with your coordinate system and check report file and report plot to save and plot the data. We'll also set up a second report to monitor a global flow variable, in this case, the maximum Mach number within the domain. Once this is complete, we're now ready to run the simulation. Ensure to save the case and data files before running in the event of any issues during the solve. With the simulation set up and ready to solve, we'll look at the solution process and post-processing the results in the next video.